Following is my conversation with Professor Ali El-Sharif. We talk about both of our favorite topic, explainable AI. Explainable AI is a branch of AI that helps create plausible explanations for black box deep supervised learning models. We look at all different variations and types of explainable models, the current state of the art, its pros and cons. We also talk about explainability and what is a good explanation versus a bad explanation. We discuss David Deutsch and his philosophy about explainability and its importance. We look at artificial intelligence of today, mostly deep supervised learning, its strengths, its weaknesses, the costly need for data labeling, and the need for data trusts to emerge that are domain specific, where companies come together within a given domain to collaborate on constructing very high quality, high fidelity data sets. Because creating those data sets for each company is a very expensive endeavor. However, their need is there. We also talk about Canada, because that is where Ali is from, and how and what type of policies are contributing towards Canada leading AI. Ali offers a lot of advice for practitioners learning explainable AI or XAI. And now, here is my conversation with Ali El-Sharif. Hope you enjoy. How are you, sir?
I'm doing well. How are you, Amjad?
You know, very good, very good. I am so excited and looking forward to our conversation today. I'm fascinated by the need for high quality, high fidelity explanation, explanatory power. I'm just really in general a fan of finding good explanations, whether in engineering and science. So when I started interacting with you and your passion and research in this field, I thought it just would be awesome to talk about it in the context of both engineering and business. I mean, this is a developing field. So maybe you want to start a little bit with explaining your passion into this area, and then I know that you have put together a set of slides for us. Then we'll, in a very interactive fashion, go through that. So no, exciting stuff. And Ali, over to you, sir.
Thank you, Adarsh, for the invitation, and I appreciate the introduction here. Absolutely, I'm super passionate about the area of explainable AI because of the promise of artificial intelligence in helping us make better decisions, and the realization of that promise is contingent upon us understanding what these AI models are doing, and unlocking the mystery of what AI models are doing on our behalf when we're deploying them in high stakes decisions is something that I find super intriguing, and it's one of the prerequisites for us to adopt these AI models into important decisions.
So true.
Absolutely, absolutely. The title of the presentation that I have is Trusted AI Decisions with Explainable AI. And what I'm going to go through here is why do we need machine learning explanations? What is explainable AI? Explainability, why so difficult? And some explainability options. And then we're going to go through one of the more popular methods for AI. It's called LIME. Now, I'll start with what I just mentioned briefly in our conversation here is AI's promise is that it can help us make better decisions, or can make better decisions than humans. And by better decisions, we mean they're fast, accurate, fair, predictable, stable, and secure. And the realization of that promise, in my judgment, requires us to understand what these AI models are doing. So before we go into why do we need machine learning explanations, I'm going to just go over and just say, why do we need why do we need machine learning or AI in a lot of problems? And I use this little example of a tree classifier, feeding an algorithm an image and asking it to classify, is this an image of a tree or non-tree? And if we were to try to predefine rules of what a tree looks like, I bet you we would have not predicted or came up with a rule for this twisted shaped tree. Or we may have had difficulties with predefining all the colors and shapes and species of trees. Yeah, I mean, I think you would agree with that, right? And but instead, when we look at these images by intuition and just by our logic would immediately tell us, yes, this is a tree and maybe this is a flower. For problems that we can't easily define rules for, these are the problems that we want to direct or try to solve with AI, because if we feed our machine learning models enough examples of trees and non-trees, with enough training, with enough samples, they will eventually learn to meet or even sometimes exceed human level performance at certain tasks. Now, what that brings us in is examples in which AI fails to meet its promise, because when we let it loose to go figure out the solution for this problem without us interfering with its logic, it sometimes can solve these problems in unpredictable ways. And this is a particular example that I'm sharing here that has an AI model that was tasked with predicting a health outcome based on images of X-rays. So this was a pulmonary disease. And ideally, we wanted the AI model to detect the presence or the absence of disease by examining the image of the lung. And instead, the model cheated, if you will, and learned to look at text in the corner of the image, the word portable, and come up with a decision that was based on the make and model of the machine. So portable, the word portable became a proxy for patients that were too sick to come to an X-ray machine, and the X-ray machine had to come to them. Inpatient units became a proxy for patients that had their visits scheduled in advance. And then there was an emergency department unit that was a proxy for patients that needed to be seen right away. Now, with completely ignoring the X-ray image, the model was able to learn just by the type of unit that was used. This is the likely health outcome or the prospect of this person recovering from their health condition without examining the image of the X-ray. Now, with an explanation, we've had something called an activation heat map that highlighted the region in which this particular model was using for its logic. We discovered what it was doing. And the reason this is bad, right? I mean, some people will say, okay, well, if I have the right answers, why do I care if I'm right for the wrong reasons? Because if I introduce a new type of X-ray machine, or that text changes at some date in the future, my model will fail miserably, and I may not detect the fact that it did, and I can start depending on something for a critical decision, and that's completely unreliable. So I'm just curious as to your thoughts as to what we said, Anja.
Yeah, no, this is a very sort of insightful example, and to your point that at the end of the day, the current day supervised learning is curve fitting, trying to find the path of least resistance to fit input to outputs, and in that, unless we are careful, it does not take into accommodation the context. It doesn't many times, in fact, all the time, it does not know the model of the word or the broader situation that we, the human decision makers or radiologists in this case, the word that we live in and the entire context that is missing. So I think first, it is a really good example that speaks to the perils, the shortcomings of the AI. But then it also maybe points out, since supervised learning is a powerful tool, on the need, Ali, for better annotation and labeling of data, also more, attentive models where the model tries to attend to a certain part of what it is looking at and ignore others and that sort of thing. In the business world, Ali, what I'm finding out is that creating the ongoing creation of training data sets, high quality, high fidelity training data sets that are reliable and does not have bias in it, is a very costly endeavor. And in many cases, it is a roadblock for the AI projects and what have you. And another thing that we run into is where people who are knowledgeable about it in a business setting would say that no one company, no matter how big they are, can afford continuing to build these high quality training data sets for deep supervised learning. So maybe there is a need for cross industry data trusts where people share a lot of data under the right rules of safety, security, who does what, and then it gets annotated and somebody blesses the quality and endorses the quality. And then everyone in that industry uses that training data set to do whatever training that they need to do. So this pattern is very common. I'm also, so those are the thoughts that came to my mind, Ali. I'm interested in your sort of, thinking now or later in this discussion on this exorbitant cost of the constructing training data sets and the right way to maybe go about that. And then there is a rhetorical question here, you don't have to answer it, is that we as people, the minds that we have, it looks like we can learn from a few examples and we can generalize from that, and we don't need, a lot of examples. So maybe, you can only comment upon it now or later, that where do you see deep supervised learning going toward self-supervised learning or other areas where the need for the training data set or a very large training data set gets somewhat contained, and maybe the models, while they are building specific skills like reading an X-ray, have some general understanding of the world as well. There is a hospital, there is a patient, there is a doctor, there are different types of machines and things like that, whatever the meta knowledge of the situation is. So those are some thoughts that come to my mind, Ali. Over to you, sir.
Okay, so you said you made a lot of interesting points of observation, Amjad, and maybe I'll comment on a few of them here. What I would say in terms of the idea of a data trust, I think that's a wonderful idea, and we have seen examples of it in the research community, right? So today, if I need to train an optical character recognition classifier, I have pre-established data sets with images that are already labeled, and I don't need to do that from scratch. So a lot of those initiatives are driven by do exist, and they are research-based. But then I would just say they are very limited in the domains and applications. So I think in your area, you might have an interest in supply chain, or some really niche domain in which you have a lot of expertise in. What are the data sets that make sense for that scenario, and which what context these data sets can be applied to and whatnot. This is an interesting idea, and I think there's a lot of need for it, and certainly something that requires a lot of collaboration, because as you said, no one company has the scale and the ability to accomplish this on all domains, right? You might be able to solve one problem or might be able to provide one data set for a very narrow problem, but then that's just something that requires a lot more resources and interest. In terms of training or having models that can generalize well with fewer training examples, I don't know that we're heading in that direction. I think what I'm seeing us heading towards is we're achieving these gains through large data sets and throwing computing power at it. So the desire for being able to do it with less is great, but I think the frontier that we're at today is we're able to make these progress with large data sets and a lot of computing power, and that's what's driving better models today, and maybe with sometime in the future that will be different, but that's what I'm seeing today. Okay, so I'll continue on if have I addressed your questions, or
no, that is, thank you.
Okay, excellent. So I'll go on now. The other motivation or reason why we need explanations is our algorithms can be super confident when they're completely wrong. So when in this particular example in the literature, within these machine learning models that were tasked with detecting or identifying a guitar or a penguin, with the right pattern, they were fooled into classifying these incorrect images as guitars and penguins with a high degree of confidence. A more serious example is we even have things where, or a class of attacks called one-pixel attacks, where altering a single pixel on an image is enough for us to classify that image incorrectly. Now, imagine a scenario where all you needed to do to fool a computer vision algorithm that's supporting a self-driving vehicle to fool it from not detecting a stop sign is to put a sticker on that stop sign. And that vehicle no longer understands that that was a stop sign because there was a sticker. Now, that could be a way where you could cause havoc and have a lot of potential risks of people's, or it limits our ability of utilizing that technology. So understanding the logic of these models is important, primarily because we know that these models have been proven to be vulnerable to attacks like this. Also, machine learning models or an algorithm that we don't understand, if it's mimicking historical decisions, it could essentially what it could repeat or exaggerate biases that have existed in the past. So if there were historical biases in which maybe one class of people, maybe in this particular case it was a woman of color, have not been treated fairly in a judicial system, and all what we did is delivered or developed a model that repeated the decisions of the past, then all what we've done is created a more efficient bias system, right? And here's an example of Amazon trying to apply AI into their hiring practices. And they scrapped the system because of explainability, where they identified that women who were, were not actually treated as well as men in the hiring decision. So it identified, in this case, the reporting identified that if the resume had women's chess club, or if somebody went to an all-women's college, those were associated with a less likely prospect of that person being hired. So this was an example of an attempt to automate and apply AI models to recruiting, and they caught something that was inappropriate, and they stopped it. So, and in some cases, explainability is the law. And there's a lot of maturity, I would just say, in the financial domain. In this case, there's a law of U.S. Equal Credit Opportunity Act of 1974, where if you wanted to use AI to come up with a credit decision, you are legally obligated to provide that person that was denied credit the reasons for that denial. And with GDPR, there is a clause in there that's obviously the European law here, that there's a clause in here that identifies the right to an explanation. So if you, as a user that's impacted by or significantly impacted by a decision that's AI driven, you have the right as a person to ask for the logic that was used in that decision. So I'm going to pause there for a second, and then I'm just going to move to, okay, well, we identified that explanations are important, and the very reason we turn to AI to solve problems that maybe we can't properly define is the reason that they go ahead and do things that are unexpected, and we do need those explanations. So a fair question to ask is, what is an explanation, or what is explainable AI? And I'm going to go through and identify a number of sources and organizations that have attempted to answer that question. So this is a definition by an organization called Fairness, Accountability, and Transparency Machine Learning, FATML. And they defined explainability as ensuring that a decision can be explained to an end user or stakeholders in non-technical terms. So something that an end user can understand. DARPA, the US government agency that gave us the internet, answered or defined it quite nicely here in terms of questions. Why did you do that? Why not something else? When did you succeed? When do you fail? When can I trust you? And how do I correct an error? And then here is an interesting, fairly well done paper identifying that an explanation is going to be different depending on the target audience. So a domain expert, a medical professional who's going to make a decision on a course of treatment is going to need something different than the patient or the model developer, or maybe a regulator that's coming in to audit to make sure that you're not doing something that's in violation of the law, or a data scientist that's working to develop the model. So all of these are different stakeholders. I mean, and then you have executive leaders and managers that may have a different need. So that one model interacts or has with different stakeholders and decision makers, and each one of them has a different need, and an explanation needs to be appropriate for the level of knowledge and the need of that particular user. Now, so the summary of the benefits of machine learning explanations helps us validate our models, defend against adversarial attacks, detecting bias when it occurs, regulatory compliance because it's the law, and model debugging. And ultimately, explanations lead to trust, and trust lead to adoption. So an explanation is an essential pillar or an essential prerequisite to actually get us to deploy these models in high-stakes decisions. So just curious as to any, you said a lot of things. I'm curious as to your thoughts, Amjad, on what was discussed so far.
No, I am, Ali, always fascinated by explainability and how to find good explanations and characteristics of good explanations from not so good explanations. I think that is something that is, a open question in all scientific disciplines, engineering, medicine, and what have you. I would just share with you that I study this British philosopher, David Deutsch, who have, spent a lot of time thinking about explanations and what are the traits of good explanations and whatnot. And it is interesting and funny sometimes, to hear in neuroscience and cognitive psychology circles that we as people do things in our minds, we make decisions, we take actions, and then post hoc, we come up with a plausible explanation. I did this because of this. I decided this because of this and that. And it is funny that, at some level, philosophers or scientists would say that a goal or mission of AI is to reverse engineer our own minds. And so in that sense, explainability is so important because to your point, it is directly linked to trust and adoption. I know that you're going to, in the conversation ahead, we are going to talk about different ways of explainability and those characteristics of, explanation in local and other contexts. So no, it is such an important topic that many reliable methods, like even in the human brain, our perceptual methods, they are black box methods. We don't know why even our brains made a certain decision and whatnot. But once it becomes widely available and it becomes conscious, or we become conscious of it as subjects, then we also come up with explanations for that. It is also, Ali, interesting that in science, David Deutsch talks about that how good explanations, even when they are vertically localized, can help you make a lot of progress. So in a sort of poster child example of general relativity versus quantum mechanics, general relativity for the domain in which it operates is a classical theory. It offers classical explanations of gravity in terms of explaining it as space-time and not as another force of nature. And while it has created a lot of issues in terms of not being able to integrate it with quantum mechanics or other lines of thinking, general relativity as an explanation of gravity, which you can say is a black box phenomenon in nature, nature somehow does it, right? So for over 100 years, have provided high quality predictions and explanations, like your X-ray example. If done right, in case of gravity and general relativity, it provides, in a vertical setting, very high quality explanations that are relevant, they are connected, they can lead to good predictions. you can make a lot of progress with that. But the moment you leave that vertical domain, it all falls apart. And the moment you say, let's generalize it, let's unify it with this or that, it all falls apart. So no, I am just, on the topic of explainability, Ali, even the philosophy of it, I am like hugely into it. And to your point, this is, in my humble opinion, a very important area of this next phase of AI research. First of all, as you mentioned, it is the law. But then also there is a responsibility here that corporations have, because we both know that innovation and progress in capital markets, it is always ahead, and the law catches up and lags behind by quite some margin. So meanwhile, the onus is on on corporations, industry forums to think about what explainability means in their context and how explainability will lead to trust and adoption before somebody can comes in and say, I am going to hold you legally accountable for that. And we both know eventually it's going to happen, but it is going to lag behind, and we as an industry can learn from that. So certainly this is a very important topic. Those are some of the thoughts that came to my mind. As you were talking about it, I started thinking about this analogy this analogy came to my mind of David Deutsch and the philosophy of explainability and general relativity and quantum mechanics. So this issue of figuring out post hoc, high quality explanations, I think is there out there. Not most things in other domains, Ali, also, they don't have intrinsically woven explanations. They are not, a lot of other domains or methods are not, they don't offer intrinsic explanation. The explanation then come, as another step. So anyways, as you can see, I can get excited about that.
Okay.
Over to you, back to you, Ali.
No, okay, well, I'm going to comment on a couple of interesting things that you said. The biggest, there's a model that we don't understand what it's doing, we call it a black box. And the biggest black box out there is the human brain, right? Because a lot of the time we don't understand why we do what we do and what's driving us. The other interesting thing that I think you mentioned here is an explanation is a model of the truth. It is not necessarily the truth, no. But it's a model that can help us understand what the truth is behind what we're trying to explain. And even though it's not 100% accurate, it's useful for us to understand it. And I think that's we're going to see that come through in some of the ideas or options that we have to talk about. So let's jump in here. So if explainability is important, why is it difficult? And one of the reasons that explainability is difficult is that we are achieving accurate predictions through a lot of these machine learning models through complexity. So in a feed-forward, fully connected network, you have a lot of connections with just 3 layers, and all of these connections, to some degree, what was turned on, what was not, and the coefficient and the weight that was assigned for each one of these connections is part of the logic of the model. And that complexity is overwhelming to us as human beings if I'm trying to, if the explanation is everything that happened in the middle, right? Now, we have an alternative of what we just call a decision tree. And a decision tree is, I mean, in this, if I were to come up with logic for classifying a penguin, I would just say, does it have feathers? Yes. Can it fly? No. Then it must be a penguin. We would refer to these, and I used the term earlier, intrinsic or explainable by design. The structure of the model itself is the explanation. I just have to traverse true, false, whatnot, and that's sufficient for the explanation. The problem with decision trees is that human cognition does not scale. That is, if the tree that is explainable and it makes perfect sense grew beyond a certain level of complexity and depth, then what was a explainable model became unexplainable and became a black box. Even though I have access to it, it's just too long and too complex for me to understand it. And this is an interesting paper by Cynthia Rudin, which she is calling out the community for falling in love with complexity for its own sake, because it's maybe it's the hot new thing, and we may not be trying the simpler models that can actually get the job done without the need for complexity. So complexity is bad. It's not good. We can put up with it if we have to. If we can come up with a simple solution that can get the job done, then that's where we need to go first. So I'm just curious if you've seen, Amjad, any attempts or any direction or people's tendencies to fall in love with the complex solution because it's what everybody's talking about, and when we're doing so, we're foregoing simpler, easier methods that can get the job done, and they're also explainable.
No, that is very true. That many times there is this desire to go for the shiny, exotic object, and you may not need it, and but I think people who are deeply sort of, their thinking is rooted in fundamental principles of engineering and science. They know that many times, simple methods, they win the day. They are more scalable, they are more explainable, and you match the complexity of the tool or the method to the complexity of the problem.
Yes.
And many times, and I think that is a point that Cynthia makes as well, that a proper reframing, reformulation of the problem can in fact put a problem into different chunks, and the complexity maybe of each chunk is more manageable. But the point in general is that, hey, let's not do an overkill or over-engineer or over-model, because that is just a fashionable thing to do. It can lead to a lot of undesirable consequences. So I'm 100% with you, Ali, on that.
Absolutely, absolutely, and it even goes back to even if we can solve a problem with a rule-based system, don't use machine learning. So we are not, as practitioners, our obligation is to advise our clients and our friends. Yeah. Yes, this is our field that we specialize in, but maybe there's an easier and simpler way to solve your problem that does not involve the hammer that I have, right? So having said that, complexity sometimes is inevitable. And here is an example of a natural language processing model that has a large number of parameters. So the point being is, we want to avoid complexity when we can, and we're going to be good stewards and good trustees of people that come to us for help, and just say, don't go there if you don't need to. But sometimes we need to. And there's an example of natural language processing models in which complexity is inevitable. The other challenge is we should not forget about the stochastic or the randomness involved in coming up with machine learning models. When the problem space is too large, a lot of the time we would have to we were just going to start at a random point in that domain and just come up with a solution that minimizes the error to an acceptable level, which means you could end up with many different models that achieves the same level of accuracy. And each one of these models has a different set of logic or features that they use in order to come up with the answer. So a model is one way of solving the problem, and that one way could have ignored other possible paths to the same solution. So having said that, let's just talk about explainability and maybe establish some terminology to move the conversation forward. So a white box model is a model that's self-explanatory, where the structure of the model is the explanation. A black box model is one that achieves its job without us understanding the logic. Sometimes that opacity or the lack of transparency in the model is intentional to protect the trade secret or to prevent people from gaming the system. So a good reason why you want your model's logic to not to be known, for example, in the case of search engines, right? They don't publish the logic of their models in order to prevent people from maybe cheating and gaming the system into getting a higher ranking. A lot of credit agencies may not want full transparency of their internal logic because somebody would figure out the rule and could potentially maybe meet the requirement in ways that they were not supposed to. So in this context, a lot of the tools that we're going to talk about, or the methods, are discussing a black box model that is a black box because of complexity. And one of the mechanisms or options that we have for reducing the complexity is to focus on a local region. So this is on the left here. I have a model that's inherently complex, and trying to understand the entire model is just overwhelming because of the size of the model and all the twists and turns that it takes. But a single prediction, if I just focused on that might be sufficient enough of that's sufficient to support that individual decision, and the complexity of that model is reduced because I'm only focused on one decision versus the entire model as a whole. Any thoughts on maybe focusing on a local decision versus having to explain the model, Amjad, that you think maybe that is that useful, or is that something that you've seen?
Yeah, no, I think I can draw a parallel in where in general, even for very complex landscapes, whether in this case the weights of these models or whatever that complex landscape happened to be comprised of, that usually some predictions or some decisions, they are clustered in some local regions, and those local regions are compressible and have a lot of linearity to offer. So in that sense, I am having a good intuition and parallel that local linearity comes to save the day in many places. Our own physical universe in which we live has this feature of local compressibility, local linearity in it as well. So I'm just as an engineer, as a scientist, I'm drawn to the power of local linearity because it comes very handy, in many instances in a complex landscape where you can go and have a bunch of such local explanations for a few different such clusters. So I'm happy to see that in our AI models, in some of the explanation models, local linearity is being used as a tool.
Okay, excellent. And when back to our conversation earlier here, where we said a surrogate model is, or an explanation is a model of the truth.
Yeah.
We have the concept of what we call a surrogate model, where we would allow the model to achieve its complexity and achieve its results through accurate results through accuracy, and then have a model that mimics what the model is doing, when we call that a surrogate model or post-hoc explanation, and generate an explanation of what the model is doing. And then maybe a little summary here of the methods that we've talked about here is you have your explanation methods. You either get a model that's explainable by design, and if you achieve that, then you're good, that can stop. Or you can have a black box model prediction that could be a global explanation or an explanation for a black box model that could be global, or trying to explain the logic of the model as a whole. It could be local, or it could be model specific, where that explanation only works for that specific model, or model agnostic. And one of the tools we have to achieve post-hoc explanation is a method called LINE, Local Interpretable Model Agnostic Explanations. And it's a post-hoc method in the sense that it allows the model to proceed on its own with or perform its logic based on input-output pairs. And by observing what the model is doing from the outside, by querying the model, we're able to construct an explanation that is a model of the truth of, or a surrogate model of what this black box model is doing. So that might be a little bit confusing, but maybe let's just look at how this gets applied in practice. Here's an example of a model that is tasked with distinguishing between a red cross and a blue dot. And this model has a decision boundary that is globally complex and nonlinear. But in a local region, this complex model could be defined by a linear model. So this line here can explain why a particular decision point was a red cross versus a blue dot, and can do so fairly well in this local region. And if I was interested in a local explanation, I could just ignore what the model is doing globally and just focus on a local region here. So to do so, a method like LINE will take a model as a black box, take the input instance that I'm interested in explaining, and randomly sample around it. So think of some sensitivity analysis, where if I remove a particular feature and observe what that model is doing, and if that removing that feature has a big influence on the model prediction, then that must be an important feature. And if it has zero influence, then it's not important. So through that technique of selectively randomly sampling around that particular instance and observing the behavior of the model in response to these random perturbations, LINE is able to construct a linear model that is a simpler version of the truth. So in reality, this black box model has a complex model in it. And we don't have visibility into what this complex decision boundary is. We only know that there was a point that we wanted to explain, and we observed what the model's output is depending on based on different sampling of the input. And based on that sampling, we constructed a linear model that we know is not faithful to the model globally, but it's faithful to what the model is behaving in a local region. How that looks is, or how that ends up looking to a person consuming that explanation is, you end up with a decision by a machine learning model. And you end up with a list of features that either support or contradict an explanation. So in this particular case, we have a prediction that this particular patient has the flu. We have two supporting features. This person is sneezing and they have a headache. But we have one contradicting feature, that person is not displaying any fatigue. And the overwhelming on aggregate, the balance of the evidence points to the fact that this person has the flu, but I now have a list of features that I can point to and just say, these features support the prediction, this feature contradicts it, but this is my prediction anyway. So feature importance is and the directionality of these features is the form of the explanation that we get by a post-hoc method like LIME. How does this look in practice? Here's an example from the original paper in which, through different samplings of an image, they identified that the classifier was biased, that this particular classifier was tasked with classifying husky versus wolf. And instead of looking at the characteristics of the animal, the face, the teeth, the shape of the animal, what we were left with is images of, or identified that this classifier was based on looking at snow in the background. So this is a highly biased classifier. Another classifier that was used in the LIME paper to explain its logic is this text classifier distinguishing between atheism and Christianity. And this particular classifier was looking at the word edu or NTTP or just noise in the data that was not consistent with the logic of the model. And that particular example just demonstrates that this is a classifier we should not trust. So the pros of a method like LIME is it's highly cited. It came in 2016, and as a few months ago, it had over 4,000 citations in Google Scholar. Some of the, it's easy to understand and it's easy to implement. Some of the cons is it makes an assumption about local linearity, and that assumption may not hold sometimes.
Yeah.
It's also computationally expensive to come up with this random sampling around the input. By default, it needs about 5,000 samples. So for trying to construct an explanation for what the model is doing in different regions is a very expensive operations. And then it also suffers from the lack of stability, where because I am randomly sampling around this particular input space, I could end up with different explanations depending on different times I run the explainer model. So you could, and if you do so, which explanation do you trust? And then it is I mean, to keep in mind, it's an approximation of the underlying model, but it is not an exact replica of the underlying model. So sometimes the term fidelity is the level of agreement of with the underlying model is an open question. And it has been shown to be vulnerable to adversarial attacks. So if you knew what you were doing and you apply some specific techniques, it is a vulnerable tool to adversarial attacks. You could easily fool it. And interestingly enough, one of the co-authors of the paper identifying the vulnerability of LIME to adversarial attacks is one of the co-authors of the method itself. So this goes back to Samir Singh. This goes back to we should not fall in love with our tool. We should always acknowledge the limitations of it. And the conclusion about this tool, it's a great tool, very popular. Use it, but don't use it blindly, because a misleading explanation is entirely possible with these tools. Yeah. And misleading explanation is worse than, it could actually be worse than no explanation at all. And I am going to conclude shortly here with this resource with the foundation of machine learning, or best practices for machine learning, that is noted here through this wiki. And it talks about best practices. It does need to require explanation, but it requires monitoring, performance, product traceability and product management, fairness and non-discrimination. There are a lot of things that are important to address organizationally, as well as during product design and coming up with a machine learning model that's safe to deploy in the field. So I have a whole bunch of resources and books and things that can leave people with at the conclusion. So I'm going to share those with you, Amjad. But just want to conclude with this, and I just want to get any closing thoughts from your end.
Yeah, no, I think your passion for explainable AI comes across loud and clear. Certainly, as we can see, it is a field in its early life cycle, lot more work that needs to be done. So Ali, my question for you is, what uh, what is your attraction towards explainable AI research? I want to, see that what brought you to this specific discipline, and then what do you see as a road ahead for explainable AI, and as deep supervised learning and deep self-supervised learning, those things evolve? How do you see explainable AI co-evolving? And before I let you comment upon that, one thing is very clear to me and resonates very strongly with me, and that is that the complexity of the model that computes inputs to outputs uh, is generally that complexity, the model size is very large of those black box models. But it looks like that the the explainability part of it can be hopefully a little, less complex, little, more modular. And it, as an analogy, it resonates with, in a loose fashion, with human brain as well, that the perceptual processing that goes on in our cortex and subcortical regions generally is very, very complex. That model space is very complex, but the explanations, they are more, suited for the customer, the human mind. Because if the explanation is extremely complex and gibberish and does not make any sense, it will not be a good explanation for the audience, right? So explanation is for a certain audience, for a certain customer, for a subject, in order for it to make sense and for it to have some good characteristics of that you were showing a minute ago. So hence, that is a big message for me in terms of how you handle complexity, where you need, these complex models to compute these complex landscapes, these decision boundaries that are very nonlinear, very complex. But then you come up with plausible explanations, and they go hand in hand, they co-evolve. So maybe Ali, tell us a little bit about what brought you to this field, and where do you see this field going?
Okay, thank you. So on a personal note, what brought me to the field is I'm just really intrigued by AI explanations, because to some degree they are a mirror into our own brain and into our own logic that we sometimes apply without being conscious. So it to some degree, what brought me to AI explanations is what brought me to AI is they are modeled after biological systems and human. What more interesting thing than just to sometimes reflect on human cognition and what makes us do certain things. Also from an applied and pragmatic perspective, without these explanations, we are not able to safely deploy and adopt these models and things that are of consequence. So I view this as an important contribution to the field, where without it, we're not going to be able to have safely apply AI in interesting problems. In terms of where I see the field moving forward, I think definitely better explanations, right? We have a lot of work to do in a lot of areas in which we can identify where AI fails and AI succeeds. And the more complex that we are getting, that our models are getting because of the size of the data, and where the progress that we're making with AI is driven by complexity and computational power, right? So we don't have better models, we have better computers and better data. And with that leaning towards or counting on complexity to get us there, explanations are going to be a big part of it. One particular area that I see explanations moving towards is less of maybe feature importance and a list of features, and maybe more towards natural language processing explanations. So imagine an AI system that can explain a medical decision to a patient the way a doctor is able to explain it to a patient, right? Here's your context. Here's what's specific about you, and after reading all of your charts and lab results, this is what we think we should do. So if we get to the point where we think an AI model is able to have that conversation, right, with a human being and explain it to them the way that a human could get, that would be the holy grail of where explainable AI could go to.
No, that is awesome. One technical question, or pseudo-technical question, Ali, that I want to ask you is that we talked early on about deep supervised learning and cost of data annotation, data labeling, and all the challenges involved with that in different domains. Do you see these explainability models, do they have extra annotation or labeling requirements, or they just work with the currently labeled data? And as you were saying, they make random samples or subsamples from that space to build these, in some examples, locally compressible, linearizable models. I just want to ask you this. I think I know the answer to this question, but I want to, while I have you, sir, here, I want to ask you this, that are there extra annotation labeling requirements? I know that you mentioned, of course, there are extra computational requirements because you are developing another model of the truth here, but are there extra labeling requirements here?
So the short answer is no, I don't believe there are extra labeling requirements. There is maybe extra effort and extra oversight and involvement in doing so. So the short answer is no. But I go back to your thought on maybe having these feature stores or data sets that are labeled, and they are supported by a consortium of partners. Yeah. We do see I do see a lot of parallels with standards. So for example, you have the auto industry, and they can compete fiercely on products and in certain areas, but they do come together to agree upon maybe standards of whether it's cybersecurity or connected vehicles, because those standards have to be in place for everybody to be successful. So, and we do see a lot of examples of even big tech companies agreeing on maybe XML or whatever standard that's in place, because the presence of the standards allow all of these systems to interoperate. So some effort could be government-driven, it could be driven by big tech, or even by a group of concerned individuals that could just start an initiative. And it does require a level of collaboration similar to what we see in the establishment of standards and in the establishment of rules of the game that everybody has to play with in order for all of us to flourish.
I 1000% agree. I'm so aligned with that there is a need in different domains, in different industries for such collaborative models, whether you call them data trusts, whether you call them whatever, where these data sets get established as an industry effort, and a lot of smart effort goes into their construction and making sure that there is little to no bias, or there is a lot of metadata that is there. And then the practitioners in different companies, then they can use it to build reliable models. Because look, if in a domain an AI wins and it can bring a lot of prosperity to not only that company, but its customers. If an AI fails in a given domain, that not only then, those domains are left behind, but it has a cascading effect, a ripple effect to other adjacent domains as well. No one wants another AI winter, but these issues are substantial. So I think your point, Ali, is spot on, that such a collaboration is needed. And to your point, this is not the first time people are going to collaborate. We have in different industries, different domains, there are established examples of prior collaborations. You were referring to XML standards or standards in automotive, or even in autonomous driving and that sort of thing. There are standards, but I think the need for data, high quality data sets, is not going away anytime soon. And the reason, Ali, I say that is deep supervised learning, many different versions of it, your generative adversarial networks, your CNNs, your RNNs, a combination of all those things. They are very powerful tools, when applied to the right situations. So then, we have all these powerful tools. One can argue that more than 50 to 100 years of effort have gone into bringing these tools to where they are now. Absolutely. So then for us to say, oh, just because we cannot collaborate in different industries and domains to construct high quality training data sets, let's not worry about that. Self-supervised learning will arrive and save the day. I think from, since I'm in the industry and I'm a practitioner, I think there is a, limited view. There is a huge need for building these data trusts, and people have to take, visionary stand and come together in their respective domains. So wherever I can, Ali, I try to socialize this topic, that what would be the benefit to all by putting those types of efforts together. So with you. Let me just ask you a few questions, Ali, as we wrap up our wonderful, wonderful conversation. You, sir, are in Canada, and Canada in many ways is leading AI, whether all the movement in different parts of Toronto or, Quebec, Ontario, all that good stuff. And I also know that you're part of different industry bodies or alliances. So if you may want to maybe just comment upon the AI scene in Canada and how different policies are contributing to Canada being a leader in AI, I think that would be good. And then maybe, a side question, Ali, is your advice for young practitioners that, if they want to learn about explainability and other things, what would you say to somebody who's just starting? So, so would love to hear your thoughts on both Canada and your advice for young practitioners.
Okay, so well, that's a tall order to speak on behalf of the whole country, but I'll try my best. So it comes back to partnerships, Amjad, and I think we've alluded to maybe an ecosystem where potentially competitors could collaborate to establish this data trust, but it's also academic industry collaboration, government-sponsored collaboration as well. So certainly, I would just say Canada's contributions to AI, partly driven by having public policies that says this is an area or a domain that we take pride in and we want to progress in. the presence of high-quality colleges and universities in which they had some of the leading researchers. I mean, Geoffrey Hinton of Toronto and some of the other names in Montreal. So sometimes it just takes a few individuals that have made a significant contribution to the field, and then an ecosystem or a lot of good things happen around it. And just the support of a community, and I would just say maybe on a personal note, talent does not know citizenships, does not know color, does not know gender, and does not know nationality. So being an open place in which you welcome everybody, and you're open to people to irrespective of their ethnic, religious, and other attributes, and you're just that certainly attracts talent from all around the world, and certainly is a big reason why I believe Canada has made incredible contributions to this field. So partnerships between academia and industry, and a welcoming environment in which smart people from all around the world come in, and then a debt of gratitude to some of the pioneers in our field that have set the path for us. So I think that's the best answer that I can come with.
And then what would be your advice? That's an awesome answer. And of course, you have giants like Jeff Hinton and Yoshua Bengio and many, many others. So in fact, at some level, the revolution that got started with AlexNet and other techniques and methods, they all have sprung from universities in Toronto, universities in McGill universities in Quebec, Montreal area. What is, Ali, your advice for just practitioners worldwide? If I'm somebody coming from software engineering or data engineering background, or maybe even a business background, and I want to learn, I want to become an AI practitioner, and certainly AI practitioner is not one thing. There are so many different job skills and whatnot. So maybe containing the scope of my question for a software engineer who wants to become an ML engineer, what is for you as a academic person, as a professor, what is your advice to young practitioners or young students?
Okay, so young or old, right? Anybody who's coming to learn, I would just say it's important to learn how to learn, right? And focus on your ability to learn, because this is a fast-moving field, and it's an evolving field. It's been with us for a while, but a lot of developments are just happening, and it's an exciting field because a lot of new things are happening in it. So focusing on the ability to learn and have a passion for continuing to learn and continuing to develop and just be curious about this field, not because of money or glory or anything of that lot. I mean, of course, these are important things, but just being passionate about learning and really being focusing on it for the right reasons, you'll find it easy to focus on and to continue to put sustained effort if this is something that you like. So if you focus on the promise, focus on your contribution, focus on what you think you can achieve by being helpful to others, and then other things will fall into place, because if you have those basic passion, the effort that is required to get good at this is going to be easy to sustain for a long period of time. So that's my advice.
No, look, this has been a fascinating conversation, very practical, very pragmatic. Thank you for being, Ali, so gracious with your time. Really, really appreciate it, sir. This is going to be awesome for people who will be listening to this, and so there are so many ways people can take practical lessons from this conversation. So thank you.
Thank you, Amjad, so much for hosting. I appreciate it very much. Take care.